Okay, so this linear regression chapter has begun, and this another thing, yeah, and about the normality also. One was randomness, means that was the test of independence of x and y. So, so if the error terms are random, it's it meets the assumption that x and y are not means they are independent, or at least the distribution of error terms is normal. Now, the normality is only of error terms. What about distribution of x and y? Well, y is always predicted. So if it comes from normal distribution, then y will also be normal, since it has been predicted from normal distribution. Uh, so normality is the problem for all samples or only of certain samples. Like if
Sir,
you have yeah. Okay,
means,
let me explain it clearly. If the sample size is 35, then can it come from non-normal population? And will that be a problem?
so, by the central limit theorem, it has to be normal.
Very good. It will be approximately normal, because sample mean, since sample size is 35, and so sample mean will be normal. So very good. So normality problem is only for a small sample
Small
sizes,
sample size.
which are smaller than 30, and there that is the problem. If the sample size is large enough, we don't, the normality assumption will be automatically met. Okay, and how do we measure the goodness of fit of regression model? That we say that this model is good. How do we? What are the things that tell us? One is the high R square, which is coefficient of determination. Second is F statistics, and third is root mean square error, or standard error of the regression. So that is also called root mean square error. We will discuss that. Okay, and analysis of variance, what it tells of sum of squares, degrees of freedom, if valued, then total sum of a square, regression sum of a square, and error sum of a squares, and their mean value. So those are, that is called analysis of variance. So ANOVA is like that. Now, introduction to linear regression. There is hardly anything for you to learn here. It is just an example that linear regression. Okay, let me go down to the equation itself, since you know almost all these. So why waste time? So variation of y, which is the dependent variable, that becomes yi minus y bar whole square. Okay. So what does this? This is the total variation. And that is the sum of the squares of total. Now, whether it is possible to explain how this total variable came. Did it come from model? That will be explained variable, and rest will be error terms or unexplained variable. So these are total variations, and let's go down. So here it is talking about total variable. Well, these data means company AB6, and ROA is the dependent variable, and capex, capital expenditure, is the independent variable. So their mean is this. So it is nothing for you to learn, because why? So, and this one is the x variable. Total variation of x is xi minus x bar whole square. So we will look at a scatter plot first of all, so that we can figure out if there is any linear relationship or non-linear relationship. So let's see a scatter plot, and this is the scatter plot. So it looks like that. It is linear, increasing linear relationship, means return on assets increases as the capital expenditure increases. So capital expenditure percentage, you see here.
So, if it has been clustered around one particular area, then linear regression won't work, right?
Yes, then it won't be linear regression. Yeah.
Yes, sir.
Why will it not be regression? Linear regression, because clustering at one place tells one regime, and at another place it will be another regime. So either that period, or if there is only one clustering, means it was a regime around which the clustering happened, and after that the regime ended and the distribution can be random. Even though there is no second clustering, but still we cannot use linear regression there because of heteroscedasticity. So clustering, if there is clustering at one place, any one place, means there is heteroscedasticity. So we will have to fix that first. Okay, so from here it is the scatter plot, and we go down. Okay, dependent, simple linear regression, identifying the dependent and independent variable. You identify this very well now, that which one is explanatory, that becomes independent variable, and the one which has to be estimated or forecasted, that becomes the dependent variable. So, so this one also you are very much familiar. Okay, so here is the question, and then you can see whether you can, well, you can easily identify. It is not that, yeah, please read it.
An analyst is researching relationship between corporate earnings growth and stock returns. Specifically, she is interested in whether earning revisions are correlated with the stock price returns in the same period. She collects 5 years of monthly data on earnings per share revisions and stock price returns for a sample of 100 companies. What are the dependent and independent variables? Uh, Sir, she wants to whether earnings are correlated
Yeah,
with.
what is he collecting? She is interested in whether earning revision are correlated with earning revisions, or means earning is published.
Publish. Yes, sir.
Quarterly earning, it is published.
So,
So,
stock
yeah,
price is the dependent variable
very
and
good.
earnings per share is the independent variable.
Yes, that should be the answer. Let's see. The dependent very monthly stock prices. Very good. Estimating the parameters of a simple linear regression. So yi, which is the dependent variable, is equal to b0 plus b1 xi plus epsilon p. There is nothing for you to learn here. So because b0 is intercept term and b1 is slope, so there is really nothing really to learn for you. Now, what does b0 mean? Does it have any meaning or no?
B0 is when x is 0. So,
Very good. So, but does it
say,
have any meaning or no? Means it can have good meaning when x is equal to 0 at some places, and at other places,
sir, for example, if we are seeing the GDP and unemployment relation, and like when unemployment is 0, what is GDP? That could mean that is an
yeah,
ideal level of
yes, yes,
GDP.
yes. So here it has meaning.
Yes.
Because unemployment can be 0
Uh,
and the GDP will be maximum at that time.
that point.
So here it has meaning. But if we are measuring money supply and inflation, in that case, because inflation is the dependent variable and money supply is the independent variable. So in that case, can money supply be 0?
Sir, money supply can not be 0.
Cannot be 0. So
It has to
there
be some positive value.
some positive value. So there the intercept has no meaning.
No meaning. Yes.
Yes. So you have to understand that where it has meaning. But yeah, if we study growth of money supply, then growth of money supply can be 0. So if we are taking X as change in money supply, then that can be 0. And so there it will have meaning. But if we are measuring quantity of money, then it can never be 0. So it doesn't have any meaning. So intercept term is basically uh, mm, dependent on the model. So where it can have meaning or where it cannot have meaning. Economic justification, fitted regression line. Okay, so based on this data that we had, mm, ROA and capex. So capital expenditure and return on assets. So return on assets is the dependent variable and capital expenditure. On this, the straight line was fitted. Observed values are these green ones, and regression line is the dotted line. So we go down here, and what is the function here? Okay. So the residual is this yi minus beta 0 plus beta 1 hat xi square. That is the residual, or yi minus y bar whole square. So this is also yi minus y bar. So y bar y hat, sorry, yi minus y hat whole square. Now this one is what? Yi hat is there. Is it total? Okay, it is already written sum of a square of errors. So it is not a standard deviation, it is a standard error. Means the one which has been unexplained by the model. The standard deviation will be yi minus y bar whole
Bar
square.
also.
Yeah, that will be the total errors, total sum of error,
Total sum of
and
errors.
divided by n minus 1 will give the variance. Yeah.
Yes.
But here it is yi hat, so it is a standard error. Sum of squares of a standard errors, it is a standard error required, which is sigma ei square. Means this part is unexplained. This error term is unexplained by the model. Uh, okay, so they are the vertical distances. So let's go to the data. So error term is here already. Vertical distance means here. This error term will be vertically measured. Here also it will be vertically measured. Means this will be the exact value of x. So
Yes,
from
sir.
here, yeah, so this is the observed y. This is the one predicted, this is y hat. This one is yi. At this point, it is yi hat, and that one is the error term. So that's one. Okay, where is y bar?
Y
Now,
should be somewhere
yeah.
middle.
So here it is, okay, let's say it is starting from 5 and max is 20. So, and how many observations are there? So y bar should be in the middle of that. So 15, 12.5 here. So if we draw a straight line from here to here, this will be our y
Y
bar.
bar.
And obviously opposite of this will be x bar. So this is our x bar, and this one is our y bar. Now, what does this tell? So, this part, total variation is less than the error term, means unexplained variation. So, in this case, total variation is only this much. Total variation at this value of xi means when x is equal to 5, the total variation.
So that means it is understating the variation.
No, it is understating the error term. Variation, error term is overstating the variation, or variation is less than the error term. That is what it means. Means you see, no, the total variation means yi minus y bar, because this is y
Yes,
bar.
sir. So it is
Yeah.
lesser
Oh
number.
no,
So
sorry. Yi is this one. Sorry, this one
y
is
yes, sir.
yi is this one. So this one is your yi minus this one is total variation. This one is total variation yi minus y bar, and this one is the error terms. So it means
Error is overstated.
error is overstated. Yes, error. Here, what has happened? Uh, Total variation in y. This is y. So total variation in y is this one. This one is the yi minus y bar. This is total variation. And here also
So
the
overstated.
error is more. So error is
Overstated.
overestimated. Yeah,
Yes, sir.
error is more than y bar. So means this is the uh, what error is more. So overstated. Here it is underestimated. Like here, yi is this much. So error is only this much. And okay, yi minus y bar. So yi is this here. So here yi minus y bar is much bigger. This part. This part is yi minus y bar. Yeah, yi minus y bar. So here error is underestimating the variation, or the model is at this point. It is, I would say it is. Yeah, at this point, this model is explaining less than the total variation. Total variation is more than the error variation. So, so yi minus y bar will explain only one point, and that will be used in estimating B0. So yi minus y bar, xi minus x bar is used for estimating B0. B1, we estimate this model yi hat. So y bar minus yi hat. Yi hat minus y bar. That will give us the slope B1. And error term is yi minus yi hat. So, and yi hat. So there are two concepts. One is yi minus yi hat. This one is y hat, and this one is yi. So yi minus y hat is the error term. And y hat minus y bar, or y hat minus y bar is the explained term, or because y hat has already explained. Anyway, so let's go. And when we actually solve, so that is what it is telling. The model is predicting the difference. The model is predicting the error terms because it is measuring yi from yi hat. Total variation is only from one point because it is from middle. So standard deviation will be that from middle, and means from y bar and x bar. While okay, so B1, how do we calculate the B1 hat, where that is the slope of the regression line?
Yes, sir.
This
Covariance by variance.
xy and by variance of x. That is the beta. We had discussed it,
Yes, sir. Yes,
But
sir.
what is the difference between correlation and beta? That correlation is covariance divided by
Sigma x square, whereas
sigma x and
core
sigma y. No, sigma x square
sigma x square is
is the beta.
beta.
Yeah. So correlation is R is like this.
So
So R
correlation is
is equal to covariance
covariance divided by
xy.
sigma x sigma y.
Yes, xy divided by sx
Yes, sir.
and sy. So, and here it is sx square.
Yes.
So when will R be equal to beta? When sy and sx are equal.
Equal. Yes, sir.
Yeah, then R will be beta. Otherwise, beta will be different from R.
Yeah.
Okay. So,
Sir, in other words, like correlation tells how x and y are related, but beta gives the actual magnitude of their relation.
very good. Perfect definition between, perfect distinction between R and beta. Yes. So beta 1, so since n minus 1 is cancelled, so
Yes.
yeah, beta. Now, how to calculate beta 0? So beta 1 formula is very clear. Beta 0 is y bar minus beta 1 and x bar.
Because x bar and y bar lie on that line, so we can directly substitute.
Yes, directly substitute that, and then you will get beta 0. So beta 1 times y bar minus beta 1 times x bar. So in the exam, you might be asked to calculate beta 1 hat and beta 0 hat. And many people don't know this actually. Many people fail how to calculate this beta 0 from the data. Or there will be, so here is the actual data, and return on assets, and capex is the independent variable xi. So this has been, so this one is covariance. Okay, how many are there? Are only 6n, so variance will be divided by 5. Oh no, there are, yes. So here is the sum of all these three mean. Okay, we got this. So what is the slope coefficient? How will you calculate slope coefficient from this data?
Summation, this 153.3 divided by
The xi minus
122.64.
yeah, divided by
122.64.
122.64. Yes, xi minus x bar. So
Uh,
variance x. Yeah, this one is not variance x. This one is variance x times n minus one, and this one is covariance times n minus one. So that's why n minus one, n minus
they'll
one.
get cancelled.
Yeah, they got cancelled, and that's how you calculate. And intercept b hat. So we got x bar is this one is what y bar. Y bar minus beta 1.25 times x bar 6.1, and we got b0. Okay. In fact, this question was asked in Indian Economic Service exam also. Calculate beta 1 hat and beta 0 hat. And so our model becomes yi hat is equal to beta 0 plus beta 1 xi plus epsilon. And r we already explained here, so no need to repeat that. Okay, now sy. Sy is the standard deviation of y, so yi minus y bar whole square divided by n minus 1 under root. And this one is 6.92. And Sx is equal to 4.92. So, can we calculate beta using this information? So, we know R is 0.8945. Okay. Can we calculate beta? So, we know R. Okay. So, let's try it. Beta is equal to R times Sy divided by Sx. That is what we had figured out.
Yes, sir.
So, you have calculated, then see. So R is 0.8945
Yes.
times
0.894.
uh,
0.8945 times SY is 6.9210.
92 divided by Sx is 4.95. 4.9526. Did you get this?
1.25.
Yeah, so that is what beta is. Here is the 1.25. Let's go up. Yes, here. Beta 1.25. Yeah, here. So, that way, so this one is an important learning, because in the exam, they will give you beta and they will tell you to find the correlation. So actually, I hadn't learned this until I was CFA level, until I prepared for CFA level 3. Otherwise, I hadn't learned this. So in PhD also, they didn't teach me this simple thing. They taught R, and if I ask them what is the difference between R and beta, first of all, beta was made such a big hype that in regression books, that 80% of the students didn't understand. Oh my God, what this beta is? And then those who understand, they didn't know that beta was actually correlated to, highly related to correlation. So we would calculate correlation separately of the same data, and we would calculate beta also, but we didn't know how to link both of them. So you have got an advantage that you learned it much faster. That if you have given beta, and then you can easily calculate this R, because you already know if beta is there, then Sx and Sy will definitely be there. Only R will not be there. So you don't have to even calculate it that way. Just multiply beta. So how will you calculate R if you have been given beta? So how will you calculate R? So if
Beta into Sx by Sy.
that's it. So you can easily calculate, convert one another. Okay. So how do analysts perform simple linear regression? And here are the packages. In Python, use the SMOLS function, stats model package. Okay, so this one is different. This is not a scipy.stats. This one is sm.ols, and then in Python. Okay, so let's see what is the code here. And for correlation also, okay, in correlation it is usual. Python use the core coefficient, core coef function in NumPy library. Means for example, to import NumPy as NP, and then core F. That way you will do this. In Excel it was easy, equal to core L, and in R also core function is in the stat library. So that's how you will use while coding. Interpreting the regression coefficients means the beta zero doesn't make sense. Doesn't make sense in some concept. Beta zero, that is what it tells, and beta one tells that as the independent variable x is increased by 1 unit, how much means it is variation. So there is variation in x because it has been increased by 1 unit. How much will be the variation in y? So it tells us the variation, dependent variable. Okay, the return on assets makes no capital expenditure. Let's see, what does it tell? Beta estimation of simple linear regression model, calculation of dependent variable and residuals of the ROA. So this one is yi hat. So from this yi minus yi hat, 2 minus 1 minus 3. So residual E1. So E1 is yi minus yi hat. So that
Sir, the other name of error is just a residual, right?
hmm?
The other name of error is residuals.
Yes,
Okay.
is the residuals. Yes, the residuals is the name of the error term. So the sum of this will be 0, and so mean will also be 0. Here it is, yeah, error term, because yi minus this beta 0 hat plus beta 1 hat xi plus error term, and you have done this many times. Okay, here it comes the cross-sectional versus time series. So in cross-sectional, we use different kinds of data. Time is fixed and the variables are other than time. And in cross-section, the variable is fixed, but only time varies. And in cross-section, time is fixed, the variables vary as per region, as per qualification. So let me see, this is the question set. No. And if you can answer both, oh, it needs to be calculated. What do you want? You want to calculate or move forward?
So this is cross sectional, no, sir.
Yeah, the cross section, yes.
Like,
Means you will have to calculate xi minus x bar, then yi minus y bar, and then covariance xi minus x bar times yi minus y bar, and then do the same thing. It is not okay, such as if you want to see what has happened, yeah, here the same thing.
okay.
You don't need to do this, yeah,
Okay.
because you know how to calculate a standard error and a standard deviation and these
Sir,
things.
but in the exam, will they ask the entire thing? So, like, it will be very time consuming, right?
No, they will give you, I think, these values. They will give you
From
all
this, if they ask some
the
interpretations, then that.
yes, they will give you already calculating SX, XY and SY, those things they will give you. Like they will give you beta and they will ask you to
Okay,
calculate
okay. Yes, sir.
correlation.
That makes sense.
Yeah, or they may give you correlation and beta and might ask you to calculate a standard error of
Data division. Yes, sir.
yeah, that way they will ask you. They want to test your understanding. Otherwise, this one is quite consuming, time consuming. This one is quite time consuming. Okay. Because you need to calculate all the three things. You need to calculate Sx, you need to calculate Sy, you need to calculate covariance. Then only you can calculate beta and R. So, what is the intercept of this? Okay. So, from here, you have been given B1. So, can you calculate intercept? Suppose you are given this data. Then, how will you calculate beta 0? Beta 0 hat. So, can you calculate from this? Beta 1 is already given.
Sir, it is just
Yeah.
averages of X bar and Y bar. So,
Yeah. So this one is the average of Y bar. This
bar.
is Y bar,
Okay.
and this one is X bar.
So 7.5x minus 6.75.
But you need to multiply by this beta as well, no? This beta 0, B0 is
Ah, yes, sir. Beta 0 is equal to
Y bar minus B1 X bar.
B1 X bar. Yes, sir.
Yeah, that's what you will have to do. So B1 0 is equal to, so I don't need to write, no?
Okay. No, no, no. Sir.
No need. Okay, you have to calculate beta 0 at some. Beta 0 means Y bar minus beta 1 hat times X bar. So it came out to be 16.5 intercept term. How is estimated? Linear regression 16.5 minus 1.3 xi plus epsilon I. What is the pairwise correlation between NPM and RDR? So you have this beta. Can you calculate correlation? So beta 1 is 1.3. Is there a standard X? It is not there. Has it been calculated? No, it has not. It has been given, but then you will have to divide it by 7. And then you can calculate a standard error. No, this one is
Sir, but
actually,
7 and 7 will get cancelled in here. So,
yes, they
so
will get cancelled. So you don't even need to do this. So
uh,
covariance
39 by 30.
39 by xi minus x bar whole square means, yeah, 39 by 31. Oh, beta was already calculated. Then what it is asking? Oh, it is asking to correlation. So how will you calculate?
Correlation
Yeah,
is beta into Sx by Sy. So,
yeah. So you don't have no Sx and Sy.
Sx is
That you will have to calculate. I mean, divide this by 7 and take the square root, and then you can.
okay, yes, sir.
Yeah, that's it. Yeah, same thing. 39 by 7. Yeah, so yeah, here you have to calculate this.
But anyway, those also will get cancelled. Root 7, root 7.
Root 7, yeah, that will cancel. So 39 divided by 7, root 71.5 and root 30. Yeah, yes, this could have been. You didn't even need to calculate the sex. Root of this and root of this. Yes. So 39 divided by root of this and root of this. That way you can calculate correlation.
Sir, is root A into root B same as root AB, sir?
Yeah. Root A times root B, root AB. Yes, definitely. There's no doubt at all in that.
Okay.
Means you can multiply both these and take the square root. That's it.
Okay, sir. Okay.
Yeah, you don't have to take root 2 times. Assumptions of the simple linear regression model. Okay, so what should be the assumptions for simple linear regression? So two we had already discussed: linear normality of error terms and independence of error terms. What should be the other? Only for linear regression, it is not multiple. So multi-collinearity assumption will not be there. Yeah, it is only about the simple linear. Sorry, it is simple linear. So what should be the other assumptions?
Sir,
Yeah.
best linear unbiased.
Unbiased estimator, yeah, that is there. So what are the assumptions of total assumptions of multi-collinearity? That error terms are IID, means independently and identically distributed. So identically distributed means homoscedastic.
Homoscedasticity. Yes, sir.
So that will be one assumption. Yeah.
Yes, sir.
So homoscedasticity will, and then linearity, since it is blue, so linearity, I had already offended. So linearity, homoscedasticity, independence will take care of autocorrelation, means no autocorrelation. Independence means no autocorrelation. Means if autocorrelation is not 0, means the error terms are not independent. So if we say no autocorrelation, means we are saying that the data is independently, error terms are independently, not data. Error terms are independently distributed. So the autocorrelation problem happens when the error terms are not independently distributed. And what does it mean not independently distributed? The mean will be 0. Then how to estimate that, how to say that they are not independently distributed? because
So,
whether
uh,
independently distributed or not independently distributed, the mean will be zero of error term.
hmm.
So how to say, if you look at the scatter plot, how will you say that this is not independently distributed?
If it's clustered, sir,
One is, okay, the
the-
clustered will be X items. Okay,
oh,
error terms will not be clustered because X items will be clustered. No. Uh,
oh, sir, that is for homoscedasticity.
Homoscedasticity, so clustered, there should not be any cluster. Yes, that is for homoscedasticity. Clustering is also for homo. So how will you know that they are random or independent? Means the error terms are random and independent. They both or no autocorrelation.
Uh, Sir, the correlation values, R values.
Zero, yes, that's fine. Correlation value is zero, that will calculate. Then you will know that yeah, it is not it is not correlated. But without calculating, looking at this scatter plot, how can you detect it?
So, in the plot, non-stationarity, something like seasonal or trend or like.
That will tell you, non-stationarity will tell you the data, the X variable is having trend or not. We are talking about autocorrelation of error terms, means error terms are independent. How will
So
you?
it should be randomly plotted around the mean.
Yeah, so how will you check that it is not randomly plotted from the scatter diagram?
Sir, if there are large spikes away from the mean,
There are,
large spikes away from the mean.
yes, lakhs spikes away from the mean, means there will be 5 positive or overestimation, and then followed by 4 negatives, underestimation, or there might be at the bottom all are all are overestimation, and at the top all are underestimation. Then error terms are not independent. That way you will check, means yeah, if there is a series of error terms, either positive or negative, then you can figure out that yeah, it is not random. Okay, two can be positive followed by one negative, then again two positive followed by three negative. That kind of thing will tell us that the error terms are random or
Sir,
independent.
what is the difference between correlation and autocorrelation, sir?
Autocorrelation means it is related to itself. The error terms are related to error terms. That is autocorrelation. And correlation means the error term is related to some other error term, like X and Y. They will have correlation. But X1, X2, X3 means XT minus 1, XT 0, XT plus 1, XT plus 2. That will be autocorrelation. Means X variable is related to itself. That is what autocorrelation is. Like the profits of a company. If the company has made profit last year or last quarter, most likely it will make profit next quarter also. And if it has made profit in 2 quarters, most likely it will make profit in the third quarter also. And if it is a loss, this loss may continue. So the profit is correlated to its previous value, which is correlated to its previous value. So that way, that is autocorrelation, means correlation with itself, with the same variable, with under different times. That will be autocorrelation.
Sir, so here the assumption of independence, like here we assume the error terms are not correlated with itself.
Very good. They are not correlated with the previous value. Means if they were positive, they can be negative next time.
Oh, okay, sir.
They are like coin tossing. Of course, there will be two heads, but or three heads also it can happen. But then if there are 5 heads, means there is
Okay.
definitely autocorrelation.
Oh, okay. So this is the reason why linear regression can't be done on time series values.
Yes.
Because it is in most cases the errors are related to
Auto,
previous error value. Okay.
yes. So that's
Okay, sir.
why
Okay.
you cannot have this time series. That makes the data non-stationary.
Non-stationary. Sir.
Okay. What if we have seasonal variation? Means in every month of what? If we are studying sales, then during December, January, marriage season comes, November, December, January, sales will be higher. Then after that, sales will be lower for the another 9 months. So November, December, January, when marriage is at peak, the sales will be higher. That will also cause autocorrelation. Means error terms are no longer random because the data error terms of these 3 months will always be positive than the mean. They will always be above the mean. So seasonality is another reason for autocorrelation.
Yes, sir.
Yeah. So linearity means we have this y is equal to
Sir,
b.
but in case of X and Y, can they be autocorrelated or they also should not be autocorrelated?
What in case of
Like X and Y, can X terms be correlated
x
with
and
their.
y, the data,
Ah,
they will be correlated because there are two different variables. X will
X and Y will be correlated. So like, but like
yes,
X terms, if they are like, let's say the seasonal data itself.
yeah, that is, so
Uh,
yeah, so x is autocorrelated. Yes,
so,
in that
so that
case,
will also violate the
stationarity condition. Yes,
stationary condition.
or well, x doesn't have to be independent. So independence doesn't apply on x; it applies on error terms. So x itself is non-random. But yeah, it will violate the condition of autocorrelation.
Sir, but here our basic condition should be the residuals are uncorrelated, but not for the X's and Y's.
Yeah, they can be autocorrelated, yes. So long
Okay.
as residuals are uncorrelated,
Residuals, okay, okay, yes.
yeah. So long as residuals are uncorrelated, the distribution, we can test, use Z test and T test.
Okay.
Yeah, so we use T test when the variance is not known, and we use Z test when variance is known. So that is the difference. So linearity means it doesn't have to be like this. Yi is equal to b0 times e to the power b1 max. If it is there, then it is not linear, non-linear. So is non-linear in the parameters, estimating that. Okay, so if they are non-linear in parameters, so what are the parameters in regression? All betas. Beta 0, beta 1, beta 2, these are parameters. Xi, yi are and error terms are variables. So, and of course, a standard deviation, a standard error means all these are parameters. So it is telling that if the relationship between independent and dependent variables is non-linear in parameters, so estimating that relation with a linear regression model will produce invalid results. It tells the model will be biased if the parameters are related, because it will under and overestimate the dependent variable at certain points. So that's why in the linearity, the relationship should not be any non-linear. It should be linear only. If it is non-linear, then it will be up and down. So let's look at the example and you will understand it very well. Here, it looks like what? Parabola? From here, yeah, wide parabola. This relationship. If you
It
draw
seems to be something exponential.
exponential, yes, or exponential, either parabola or exponential.
Uh,
So it is exponential. Now, at this point, all the error terms are overestimating because they are, oh, sorry, underestimating.
Underestimating.
Underestimating. And here they are overestimating. Like, does it tell what does it write? So you can see that this line doesn't fit this relationship well. For lower and higher values of x, the linear model underestimates y. So here y is being underestimated for lower value of x, and whereas in the middle the linear, and here y is overestimated, means y hat is above this. Here also this estimated y means y hat is lower than actual y. So here and here, the y hat is less than actual y means it is underestimated, and here in the middle it is overestimated because the relationship is exponential. Okay, well, we had already discussed that. Another implication of this assumption, linearity assumption, is that independent variable x must not be random. That is, it is non-stochastic. So if the independent variable is random, there would be no linear relationship. So if x becomes random, then there will not be any linear relationship between the dependent and independent variables. Okay. Now, what it is, okay, here, when we look at the residuals of a model, what we'd like to see is that the residuals are random. Okay. So here, residuals are random or no? They are not random. They are like parabola. So they are non-linear. The residuals should not exhibit.
Sir, so in most cases with the scatter plot itself, we can say whether regression is an ideal step or not. No?
Yes, yes. Yeah. Only look at the scatter plot, that will give you a lot of information. The
Okay.
scatter plot, only by looking at it, you can say whether the regression, this is an ideal case of regression or not. And well, you have to still regress. So you have to make the situation ideal. And that is what Lasso does. Though OLS you can do yourself manually, Lasso will automatically make the data regressible.
Sir, will we be studying Lasso also, sir?
Not in this chapter,
Oh,
because
okay.
it is only linear regression. Lasso will be for multi-linear, probably it will be level 2.
Oh,
Because
okay.
here I didn't find Lasso. This is
Okay.
the only chapter of regression, but it has given a lot of information on linear regression. So you will understand here very well.
Okay.
So first thing about linearity also, first thing you will learn that x variables are non-random, and if they become random, then the regression won't be linear. So if we are studying any linear regression, then the x variables have to be non-stochastic, they have to be systematic, they are increasing that way. Only it is the error terms which are random. In linearity, it assumes that there should be linear relationship, otherwise there will be overestimated estimation or underestimation of actual variables. Means y hat will be either overestimating y or underestimating y at different places. So that will be the case either. It should go in such a manner that all the dots are, or this least square is minimized. So that was the condition of, let's say, uh, that was the condition of linearity. So error terms should not have any pattern, or they should not have any autocorrelation. So seasonal variation will also cause non-linearity. Well, that will cause autocorrelation also. So that will not be, error terms will not be independent. So homoscedasticity means the variance is equal, and how it is shown, it is shown here. So here is, this is the model, y is equal to 0.994. Okay, now here this variance looks more, it is outlier. So short-term interest rate, and let's see what does this. You can see this situation in 12. What which situation? Here. We will refer to the first 8 years of regime 1. Okay. So here it is the discussion of two regimes. So how to, yeah, you already said that if there are different clustering, means that is the problem of heteroscedasticity. And here it is the clustering. Here is one cluster. One cluster is here, though this one is not actually a bit away cluster and outlier. Otherwise, yeah, this one is definitely the cluster, and here this one is the cluster. So these two clusters talk about different regimes. So you already had discussed this, so then I don't need to read that. And here, what is the y is equal to, that is the fitted regression.
Sir, mathematically, how we are saying it is like heteroscedasticity and it's clustered.
Oh, the variance will be different. If you calculate variance, if you calculate variance means yi minus y bar of this period and yi minus y bar of this period, whole square divided by how many n? 8. So divided by 7. And here it is 7. So divided by 6, you will
Sir,
get different
but
variance.
usually we do it for the entire.
If you do it for entire, then it will tell you that there is the problem of heteroscedasticity, means that will move like this. There is an example. Means what will happen? That the variance, no, you will plot variance. Here it is, variance has not been plotted. So if you plot variance, that will show a trend like this. Either that can be like this, the variance term. You have to plot variance because you are testing heteroscedasticity, or it can be even like this also. So at one place it is same increasing, then coming down. But this line is not applicable to this graph because we are not plotting here variance. We are plotting here only x and y values.
So
So if
then
you plot,
ideally it should be a horizontal line, sir.
yes, ideally it
Oh,
should be horizontal line, and variance should have around that means significant. It will not be exactly that variance is 10%. If it is 10.5, 9.75, then also it is considered equal variance. Okay, so statistically variance should be equal. Not that numerically it should be equal.
okay.
Statistically it should be equal, or the difference should not be significant. So this is the case of clustering. So this model is actually not good. Why? So let's see which is the better model. So we plot the residual. So now the residuals have been modeled. So for heteroscedasticity, we are plotting the error terms. In this plot, we indicate the distance that two standard deviations from zero means 95% confidence interval. No, two standard deviation from zero, which is the mean of the residuals for the first 8 years, and then we do for the second 8 years. So here is the plotting that you were asking. So these first 8 residuals have been error terms have been plotted, and here the band of these two means 95% band, they are clustered, and this band is much wider for the second period of error terms. So when the error terms are having wider range, means there is heteroscedasticity. The variance has increased during this period. So that is the another way of showing. You saw here residuals of regime 2. These are the residuals, and their band is they are varying much more. The error terms are varying much more, while in the period 1 error terms are varying much less when compared to period 2. So that way you can look. So what it has plotted? It has plotted residuals, error terms. So you will have to plot either the variance of the residuals or the error terms. If you plot, then you can look at their variance this way.
Okay, sir.
Yeah.
Sir, so anything, and ideally it's the light between the same levels, but
Yes. It should have been go like this. Means it should have come up to here, all the variances. Then you could have said that yes, there is homoscedasticity. So homoscedasticity
sir,
means
if you had extrapolated like this, only four values are lying outside, no, sir. So,
but yeah, four values are lying outside. Yes, that's right. But still, even the four are not very close to line. These, you see, this one is very close. This one is very close. This one is also very close. Out of these 8, 5 are quite close. Even out of these 4, only 2 is on the line and 2 are away. So yeah, 50% is outside. So definitely you can say that the variance is much higher. Is it clear?
okay.
Yeah.
Yes,
So
sir.
so if of these 4 would have been here, then we could have said that
Uh,
yes, there is homoscedasticity.
okay, okay, sir.
Yeah, all for 16 years. So here you took the 16 years and did it jointly the error term. So this one is probably a new thing that you learned, that how to detect heteroscedasticity by plotting error terms. Yeah.
Yeah, yes, sir.
Okay, and why does this error term happen? Because of this regime change. So then only they will change. Otherwise, in the same regime, the variance will not change. So you said two things. If the xi terms are have making clusters, so first detection you can look here at just xi term. These are the xi terms, no rate of inflation. These are xi terms. So if xi terms are clustered, even though if they had been clustered here, means same here and here, then also heteroscedasticity should be there. It is not that there won't be hetero, unless they are uniformly distributed. The scatter plot is uniformly distributed around the regression line. Heteroscedasticity is the problem. So one test is this, and second test is that you plot only the error terms, and then their variance will change. So if I try to cover, what kind of graph do I get? Like if I try to cover by yellow line, so I try to include all. So from here, it is coming like this. Yeah, now I have included. And from here, if I take the upper band also, well, I should start actually. Okay, let me take the upper band. Then also, it is coming like this. So, okay, I should have put it a slightly touching this. Anyway, so this shows that the heteroscedasticity because the variance of the error terms is increasing. That itself shows it is not going a straight line, so it shows it is increasing. So that's how you test heteroscedasticity. And then what is this about? Fitted regression for the two regimes. So if the so there should be two different regression lines. Since we cannot include both, otherwise all our parameters will become biased. What means x bar will become biased, y bar will become biased, and all the betas, all the standard errors, and all the correlation are. That will all the parameters will become biased if we don't fix this heteroscedasticity problem. And so if they are biased means our decision will be wrong. So now what has happened? This is regime 2 regression line. It comes to be minus, and the regression line 1 is plus. So the slope is actually plus, and this slope is actually minus 0.2805x. What was our joint regression? Our joint regression was slope was 1.1979x. So it means it shows that it looks like that y will increase if x increases. But here under regime 2, it is telling that y is actually decreasing. So uh, so regime 2 looks bad because what are the regime? Interest rate and short-term interest rate, and this one is rate of inflation. So here the rate of inflation has decreased. So this is good. And here the rate of inflation has increased with short-term interest rate, even though inflation is increasing and short-term interest rates are also increasing. So it is telling this one is dependent variable, interest rates are dependent, means inflation increased and the Fed took also all the Fed further increased interest rate, but it failed because inflation should fall with the interest rate. So this model looks a success that interest rate has fallen and here inflation is low, but what inflation has increased and interest rate has fallen. Which model is wrong? Look like model 2 is wrong because if interest rate rises, then if inflation rises, then interest rate should go up. And here interest rate has gone down. So this policy looks wrong. But anyway, this is the period of low inflation, so it doesn't matter because this is still less than 2%. So this one is actually doesn't matter. Here it matters. So here it means that as inflation increases, Fed is increasing short-term interest rates. So this looks like the conventional wisdom that central bankers follow. And here, since inflation is very low, so even though it increased from 0.5 to 1%, the interest rate still went down. So I know I won't say that this model is wrong. Actually, the relationship is opposite, but but it doesn't matter because inflation is very low. Independence, we already discussed that the error terms should not be. So we assume that the observations y and x pairs are uncorrelated with one another, meaning they are independent. So if there is correlation between observations, they are not independent and the residuals will be correlated. So the pairs of x and y being uncorrelated is tested by if the residuals are uncorrelated. So this one is the assumption that the residuals are uncorrelated across observation is also necessary for correctly estimating the variances. So what is the problem? When the pairs XY are correlated or error term, the problem of autocorrelation is that variances will be biased. Now, in what way will they be biased? Will they be higher or lower? Let me see. So therefore, we need to visually and statistically examine the residuals of the regression model. Okay, so what will happen if variance is biased? Our Z test and T test will fail because T is equal to beta I divided by variance of I. So since variance is biased, so our t-test will not be reliable. Means we may make type 1 error or type 2 errors in decision making. So that's why the independence of error terms or the pairs of x and y need to be there. So this is the case of 40 quarters. So we have a big data in exhibit 15. So let's go to exhibit 15. And what does it tell? Yes, here. So here, the regression of quarterly revenue for 40 quarters. So we are having observed quarterly revenue between first and third quarter. So this is the green one, much closer. And the fourth quarter is above all. So you see that this one is revenue and this one is the quarter year, so which has been increasing. Means it is non-random. Uh, mm, so the fourth quarter is having higher return each of the time, much more than, so the mean of this fourth quarter return is significantly higher than the mean of the rest three quarters. It means they are not independent or error terms are not independent. So X and Y are correlated in the sense that in the fourth quarter, Y will be higher. And in other three quarters, Y will be lower. So now what is this? In exhibit 16, residual plots means error terms are being plotted. So that was the plot of X and Y variables, and here we are plotting the error terms. So again, error terms are showing some pattern that the fourth quarter error is overestimating, and the rest of the three quarters are, they're not actually always underestimating, but sometimes underestimating, but most of the time they are below the mean. So the three quarters will underestimate Y variables and the fourth quarter will overestimate, means it will be above average. So that's how the residual plot will show the independence of error terms. So if you plot error terms and you are seeing some pattern like overestimation and underestimation, that will tell that they are independent. Let's see. In exhibit 16, we plot the residual from this model and see that there is a pattern. These residuals are correlated, especially jumping up in quarter four, and then falling back to subsequent quarter. So in sum, the pattern in both Exhibit 15 and 16 indicate a violation of the assumption of independence. Okay, is it clear? Or you have any doubts?
Oh, yes, sir. Clear, sir. Yes, sir.
Clear, okay. Let's go down.
Sir,
Then about,
so after we have made the data stationary, then we can apply OLS on that, right?
yeah, definitely.
Yes, sir. Okay.
If you have made the data stationary, then you can apply your OLS for sure. Then assumption 4 of normality of error terms. Is there any? No, there is nothing. So what no, we had already discussed about the normality of error terms. What does this book tell? The assumption of normality requires that the residuals be normally distributed. Yeah, only error terms. That doesn't mean that dependent and independent variables must be normally distributed. It only means that residuals from the model are normally distributed, and we have the properties of normality, means mean of the error term is 0 and constant variance. That only these two parameters, mean and standard deviation, determine normal distribution. Well, or if you want to go even further, then no skewness and no heteroscedasticity. What does it do? Okay. However, in estimating any model, it is good practice to understand the distribution of dependent and independent variables to explore the outliers. So if there are outliers, then the error terms will not be normally distributed. An outlier in either or both variables can substantially influence the fitted line such that the estimated model will not fit well for most of the other observations. If there are outliers and we fit the model, our model will be wrong. It will not fit well when there are no outliers. So, with normality, we can test a particular hypothesis about a linear regression model. Okay, for large sample sizes, we may be able to drop the normality assumption because of a central limit theorem. So that you had already discussed. There is nothing. Okay, question set one. What does it tell? Uh, Let me see what is the question, and then I will see if we need to solve it. Okay, it is just at looking. Yes. So based on Exhibit 17 and 18, describe which assumptions of simple linear regression analysis may be violating. Okay. So this is the plot of revenue versus time. Okay. So this one is revenue and the time. Or that is it. And what about the plot of error terms? And this is the plot of revenue. Hmm. Revenue versus time. So both are observed value, revenue versus time. Now, let's look. Is linearity assumption violated here?
Uh, sir, here tough to say, sir. Like it looks like
Linearity assumption. Yeah, looks like
it is violated.
very good. Because here it is
Exponentially
overestimated.
turning.
Yeah, it is exponential, so linearity assumption is violated.
Mm.
If linearity is violated, then automatically heteroscedasticity will be there. So that will automatically be violated. And what about independence of error terms?
So that we can't say no.
No, we can say that because they are over here. Their error terms are overestimating, and here they are underestimating. So they are not independent either.
Oh, okay.
Because during this period to this period they are underestimating, no?
Okay, okay.
And this side overestimating the beginning and then they are overestimating. So independence is also violated. And what was the last one? Normality will be violated automatically. So all four are actually violated in this, and in this even more. This one is very much clear that it is non-linear. It is like parabola. So all four are actually violated if you look at them. The correct model is not linear, as evident from the pattern of revenues in the earlier year, the 1 and 2, and later years 14 and 16, the linear model underestimates revenue, whereas in the middle years, the linear model overestimate revenues. So linearity is violated. Moreover, the curved pattern of residuals indicates potential heteroscedasticity and lack of independence of observations. Means independence is also violated, and non-normality. So n is equal to 15. So yeah, non-normality is visible, and it will work because n is equal to 15 only. So all four are violated. Hypothesis testing in the simple linear model. Analysis of variance, we look at this. So sum of squares of regression. So that will be yi hat minus y bar whole square. This we had discussed. And error terms yi minus yi hat whole square. So this one is the regression, sum of error, and then sum of squares of regression, and then another will be sum of errors. So sum of regression, sum of squares, I used to write SSR, sum of squares of regression, SSR, and sum of squares of error, SSE, which is yi minus yi hat whole square, and that is equal to total. Okay. So what is our R square? Yeah, you remember that definition?
So R square is 1 minus total sum of square. 1 minus.
Okay, from these three, what will you write as R square? Okay, I am asking you here, R.
Sorry, yi minus y cap square divided by yi minus y bar the whole square.
Then R square will be what?
Sir, you were lost for a minute. Sir.
Okay, so I am saying that how will you calculate R square from these three information?
Sir, it will be yi minus y cap square divided by yi minus y bar square.
This one, yi minus y cap whole square divided by this one. Are you saying that R square?
Yes, sir.
No, this one is error terms. So R square will be here 1 minus this SSE, 1 minus SSE.
Oh, yes, sir. Sir.
Yeah, but by SST, yes. So that will be the case here, 1 minus. Okay. Now, and what? So that will be 1 minus. Now the question is, what if you don't use 1 minus? Then what will be R square?
The SSR by SST.
SSR by square. So that is what I was asking, that R square is equal to this SSR by SST is equal to SSR divided by SST. Okay. How will you calculate F statistics from these three? F distribution. So F is equal to what?
So F is
Mean SSR. Okay. So mean SSR divided by mean SSE. That is your F.
okay.
Yeah. So that you will get F. And then root mean square error. So this one is the error term. So you will calculate, okay, this divided by n minus 1. So that will give you the mean square error. Yeah, and take the under root of that, and that will give you root mean square error. So if root mean square error is high, then also our model is wrong. So that is what these three things we use for testing. So let's see here how it has calculated. So variation. Now here it is given yi minus y bar explained, yi minus yi hat explained. So which one is the error term? This one. And this one is the total. This one is yi hat minus this one is R, SSR. because yi hat minus y bar, and this one is the total variation. So before going looking at the answer, here is the sum of a squares total, sum of error square, and sum of r square. Okay, looking at this information, what will be your r square and f? Okay, so what will be your r square here?
R square would be 191.63 divided by 239.5.
Very good. 239.5. How much does it come?
So 191.63 divided by uh, 0.8.
Point 8.
8.
Okay. Okay. Now, what will be our f value? Okay, this one we calculate r square, and then other terms we don't need, root mean the square. We need to do that. But okay. So f value. So what is the mean r? Mean of this? So how many? There is only one beta. Yeah. Beta 0 plus beta 1. So we have 1 degree of freedom less. So this one will be 5. This divided by 5 will give us the mean SSR. Okay. So for F, we need mean SSR divided by mean SSE. Okay. So what is our mean SSR, which is equal to 191.63 divided by 5. Yeah, 191.63 divided by 5. Okay, that we got in the numerator. Now, in the denominator, what are the degrees of freedom? So, in the degrees of freedom, SSE is 47.88, 47.88, and this divided by n minus 1 is the total degrees of freedom, and 1 has been already taken. So this will become n minus 2 because 1 was taken by r. So total degrees of freedom is the degrees of freedom of regression and plus the degrees of freedom of error terms. That will give us total degrees of freedom, and we have total degrees of freedom only 5. So we will divide this by 6 minus 2 because 6 minus 1 taken by this, and n minus 1 is anyway the total degree of freedom. So n minus 1 and minus 1 taken by SSR. So we will have this divided by 6 minus 2. Now, how much do we get? Which is equal to
3.2.
how much?
3.2.
3.2. Okay, so this is our F. We will see if we calculated correctly or not. So R square is measure of goodness of fit. If the test passes F test, that is the another measure of goodness of fit, and then we will go for. So we calculated coefficient of determination R square, and what is our R square? Yeah,
Point,
point 8. Yeah, very good. We calculate that. Now, what is our, so what does F test? Okay, and what is F? F test that all the betas are equal to 0 and at least one beta is not equal to 0. So since there is only one beta, so we don't need beta 2, beta 3. Okay, so beta 1 is equal to 0 and beta 1 is equal. So what is our F test? Yeah, so here MSR yi hat minus y bar whole square, and that comes out to an MSE. So we calculated F. F we calculated what is the F value here. What is the F value? Uh,
I think they'll calculate below.
they are written below where. However,
After the hypothesis.
after this, so it is T and S. No, it is not F value. Where is the F value? It should be here. Uh, have a slope coefficient. What is the F value? The book has not written a value. Okay, we will get
I
another.
think after the like
Okay, after all
two-to-the-power,
this
or all
t-test
this.
as well. Okay, so for a single variable, one thing, this R square is actually your single correlation square xy because there is only one beta. So it is a linear regression of only one dependent variable over one independent variable. So this R square is same as a small correlation square. And so correlation was 0.8945 that we can easily calculate. Now you know that if you know beta, you can easily calculate R. So, okay, so let's go down. Mean sum of a square, but formula is correct that we divided n minus 2 yi minus y bar whole square. Yi minus y hat, yeah, whole, not y bar. And yi hat minus y bar whole square. So, what is this? Yi hat minus, oh, okay, yi hat minus, this should be what yi. So sum of squares of regression divided by 1, that is what we did. Oh no, we made a mistake. We made a mistake. You know what? Since here the degrees of freedom is only 1, no. This one is degrees of freedom is actually only 1, not 5. 5 is the total degrees of freedom. So we have only one beta. So it should be only 1. Okay. Yes. Now how much will it be? 5 times of this. How
Sir,
much?
sir, sir, how is that, sir? I didn't get it.
Oh, okay. Because we have to calculate mean SSR, mean sum of squares of
Ah,
regression.
yes, sir. Yes,
Okay.
sir.
Then what is the degree of freedom? We have only one beta, no? We have
Uh,
only one B1. There is only one slope. No, it is not multi-collinearity.
oh, okay. There are only two variables, so
Yeah,
1 degree of freedom. Okay, okay.
only one degree of freedom.
Okay,
So that way we divide it by 1. That is the mean sum of a square.
okay.
And because total degrees of freedom are 5. So I even explained that we took 1, but still I wrote 5. I had explained that we took 1 degree of freedom when we were calculating sum of squares of regression.
Sir, but then in the denominator, why we still have 6 minus 2?
Oh, because because this is the error terms, no. So how many error terms are there? There are 6 error terms, no, total. So 6 error terms, the number of errors is 6. And then so we one was taken away by this beta 1, and so and then minus 1 is the degree of freedom. So since we have total degrees of freedom 5, 1 was taken away by regression term. So now error terms have only 4 degrees of freedom.
So the correct formula is mean SSR
Mean SSE,
n
mean
minus
SSE,
1 divided by mean SSE by n minus k minus.
yeah. So mean SSE, if you are saying mean SSE, that one is equal to so SSE by n minus k minus 1. So
Yes,
this
sir.
is, yeah.
Sir,
So but if you are saying mean means that is what it means, n minus k minus 1. And here it is mean SSR means SSR by k. So this one will be okay. Let me write it here. So which is equal to, let me put this here and this here, which is equal to SSR divided by K and whole. So I will put it in parenthesis, the numerator, and then whole divided by SSE divided by N minus k minus 1. So that's what this formula is actually. Mm. Okay, so now what is the value of this f? Probably it will be 5 times of 15 or something, 16.
19
It should be 16. Yeah.
91.63. So 1.64.
1164?
1.64.
No, no, no. It is 191. 191.63 times 4 divided by 47. So it should be 16. 191 times 4 divided by 47.88.
Oh yes, sir. 16.11.
15.1. Okay, so this is our F value. Hmm. So another to test, so F test the joint betas and individual betas are tested by T test. So T test is beta 1 hat minus B1 by SE B1. And here you will learn something. So to test a hypothesis about a slope, we calculate the test statistic, which is T, by subtracting the hypothesized population slope B1 from the estimated slope coefficient beta 1 hat. Now, B1 is what? It is 0 because our null hypothesis is that slope is 0. So this big B1 will be 0. And beta 1 hat, that is what we calculated. So, and then dividing the difference by a standard error. Okay, sometimes B1 can be 1 also. Means we can estimate H0 is that slope is equal to 1. Then it becomes a hypothesized slope. So to test a hypothesis about a slope, we take the hypothesized population slope big B1. And we calculate a standard error by beta 1 hat. Now, this one is a bit new thing. What is the standard error of beta 1 hat? Okay, one was we calculated a standard error. So, a standard error of slope coefficient is total standard area divided by xi minus x bar whole square under root. So, that will give us the standard error of B1, which is our slope coefficient. So, we calculate this. So that is the formula, and let's see how it has calculated. So here, how to test the t test, that you know very well, that H0 B1 is equal to 0 and HA B1 is not equal to 0. So this B1 becomes 0. So, and the degrees of freedom are 4. Critical T value at 4 degrees of freedom is plus minus 2.77. It is two-tailed test. And in Python, the code is from scip.stats import T. Oh, this we had studied yesterday. And then lower value 0.0254 and 0.9. This way. Calculate the test of T. How do we calculate T? So we had found B1 was 1.61. So 1.61 and the mean square error is 11.96. Exhibit 39. What is exhibit 39? So where do we calculate mean square error? So the variation in capex is 122. This we had to calculate. 120 means xi minus x bar was 122.64. We had calculated, and so AC becomes root 11. How does this AC becomes there? Mean square error was 11.96. This divided by 122. The variation. Oh, okay. This one was variation, means variance was 122. It shouldn't be variation, it should be variance. So then we will have, instead of variation, it should be variance. Xi minus x bar is not variation. This 122 is our variance. So let me type it. This is not variance, this is variance. So square root of this becomes 11.96. This one is variance. No. Okay. Let me check it further. What does it want to tell here? 122.64 was the xi minus x bar. Here, this part. Xi minus x bar whole square is 122. And it has exhibit 39. There is no exhibit 39. Where is this standard error of 11.96? Mm, so standard error, where was this standard error calculated? Let me see. Standard error. So standard error is this error of the slope. So, but exhibit 39 we never encountered. Let me go up. So I am on page 295. Mm, where is that standard error? Is it here? Here it is xi minus x bar, it is yi. So it is not even that for t. I want to see where is the t calculation. Xi minus x bar was, where did that go? I don't think it was ever calculated, otherwise we would have seen it. Yes. Okay. So here is the R. Mhm, mhm, mhm. Here, what is this about? YI 3 point, okay, 11.125. YI hat Y EI is 3.875. But this is for mm, I didn't see that standard error calculation. So this one is a SX standard deviation of X and standard deviation of Y. But this one is okay available. Xi minus X bar sum is 122.64. This one is available. But where is the standard error? How did it get 11 point something? It has not been calculated here. So exhibit 3. Okay, let's go down. Now it is telling exhibit 39, but there is no exhibit 39. We were at 295 page. So mm, anyway, though this software will calculate for you, but I wanted to see where is this calculation in the book. T, standard beta is SE by xi minus x bar, we figured out. Anyway, so probably the book has changed somewhere. So let's believe that this one is correct. Standard error is 11.9687 and the square root of that is 3.45. Calculate the t. So make a decision. Recall the null hypothesis is zero slope. So B1 was zero, there is sufficient evidence to indicate. So T, where is the T calculation? It is not even T has not been calculated here. Because T, okay, let's go down. We will go to the second example, but there is some error here in the book. And the T is being tested for correlation. Okay. A feature of simple linear regression is that T statistics used to test whether the slope coefficient is equal to zero and the T statistics to test whether the pairwise correlation is zero, rho is equal to zero is the same. Yeah, that we had seen since it was only one. So R square was also the correlation square and it is the test of correlation. So we had done it yesterday, the test of correlation. Rho is equal to 0 and rho is not equal to 0. And rho was 0.89 times n minus 2 root 4 and this divided by 1 minus r square under root and it comes 4. So we reject the null hypothesis. This is the test of correlation. But I was looking at how it calculated the standard error of beta 1 hat. That I was looking. Okay, but okay, here if the slope is 1, then t is equal to, now another test. that this f is the t square only for simple linear regression with one variable. Another interesting feature of simple linear regression is that the test statistics used to test the fit of model is related to the calculated t statistics used to test whether the slope coefficient is equal to 0. So t square is f, therefore uh, f is in 16, so t was calculated 4. Okay, that is what here it calculated. So t calculated was 4, 4.0017, and we had calculated fx square at 16 point something. So it is true that f is t square when it will not work in multiple correlation. It will work only in simple linear correlation, because in multiple correlation we have many betas and many t's. So f is not the sum of all t squares. Mm, okay. Now let's see here. One-sided test of slope and correlation. This is calculated for the test of positive slope. Okay. It is just here is the summary of all. And we have done this yesterday also, that it is a test of one-sided test for the slope and correlation. So slope is our beta 1, and that beta 1 slope is positive. In that case, H0 and HA B1 is greater than 0, and for correlation, rho is less than 0 and rho is greater than 0, because if beta is positive, R must be positive. And so here it calculates the same thing. Critical value of t is now 2.13. Why it is 2 point more than 4? Oh no, it is a critical value of t, because it is one-sided, so it will not be 2.77. It will be only 2.1324 for 4 degrees of freedom. For 5 degrees of freedom, it will be different. So this is a critical value. Calculated t value. Calculated t value is slope is 0. Okay. It should have been, what is the test? Beta 1. Okay. So slope is 0. So null hypothesis is slope is 0. So that has been deducted. So that's fine. So slope is, and we get t. Here also we get t. Again, there is a mistake here in the book, because it tells reject the null hypothesis. So evidence is sufficient to indicate that the slope is greater than 0. Here, don't reject the null hypothesis, even though t is 4. There is not sufficient to indicate that the correlation is greater than 0. Come on. The book has made a mistake. It should be reject. Okay? It should not be don't reject. It should be reject. So that's why I highlighted it here. It should be reject. Same decision. Reject the null hypothesis. Not why not to cut only this? Reject this. It should not be this only. Yeah. Reject the null hypothesis. That is the correct answer. Now, hypothesis test of the intercept means B0 hat or B0 hat. So here the AC calculation is our total standard error times under root 1 by n plus x square by x bar square divided by sigma xi minus x bar whole square. Your software will calculate always this ACB0 hat and SB1 hat also. The software will calculate, and this is the formula behind that. So what does it tell? If n is larger, then this will be smaller. Yes, B0 hat will be smaller when n is larger. Now, same steps, H0 and HA. So here again the book has made a mistake. It calculated t equal to 0.79. Okay, how did this 3 come? Calculate the test statistics. So here B0 is intercept is 3. So it is testing B0 less than equal to 3 and greater than 3. So from 4.87 minus 3 it has been detected. Means here It is estimating that whether the intercept is greater than 3%. Actual intercept was 4.875. So it is testing whether intercept is greater than 3%. So it deducted 3% from 4.875 and divided by the standard error of beta 0 hat. So the calculated T comes out to be this, and significant is this one. So reject, no, it should be don't reject. Because it is wrong. So don't means probably this one should have been up and that one should have been down. The book made mistake while rewriting. That is what it looks like. Because here it is reject and here it should be don't reject, but the one guy who was printing probably made that mistake because T is much less. There is sufficient evidence to indicate that intercept is greater than 3. Well, it is greater than 3, but then it is equal to 3. The T statistics is only this much, so there is some problem with this book. It shouldn't be, yes, there is sufficient evidence to reject, but then calculated T is much less than the critical T. So we
Sir,
can.
could it be because it's like plus or minus 2.132? Is the critical value plus or minus 2.132? That could be the case.
No, it is one-sided test.
Oh,
So here it writes no rule. Here is the rule. Reject the null hypothesis
if it is greater. Okay,
calculated
okay.
is greater than.
It's clearly wrong.
Clearly wrong. It is written here itself. So probably. Oh my God. Okay. So hypothesis slope. This one is about slope means the test of B1. Okay. So how do we look in the graph? And hypothesis simple. Hypothesis test of slope when the independent variable is an indicator variable. Indicator variable means qualitative, like mid size, large size, small size. These are qualitative variables. So it tests hypothesis test of the slope when the independent variable is an indicator variable. Okay. So here is the earning is the independent variable and return is the dependent variable. What it is telling? It is also called dummy variable. Qualitative variables are called dummy variables too, and they take the value between 0 and 1 only. So consider the case of company's monthly stock return over a 30-month period. A simple linear regression model for investigating this question would be monthly returns, that is return I, regressed on indicator variable earn I. That takes the value 0 if there is no earning announcement that month and 1 if there is an earning announcement. So it is the same question that we discussed earlier. So one is announcement and non-announcement. Okay. This regression steps.
Sir, but in these cases, if we take the value as 0, would that mean we are neglecting the value instead of properly representing it?
No, it is qualitative value, no. So we are not neglecting anything. We are only testing if the return is, if the earning is announced or revised, then will it increase the stock return? And if not, so it will take the value of only 0 and 1. Means if it is 0, then earning will be 4%. If it is 1, the earning will be 5 or 6%. So with the announcement, the earning.
Sir, how would it be 4% if earning is 0, sir? Because like we are assigning the value of 0, right? So
yeah, so
technically it will be
value. Means it is, if we are not announcing any earning, means no news.
No news. Yes.
No news, then earning is 4%. That is the data, actual data.
So that would be because the intercept's value is 4%,
4.
right?
Yeah, it can be, yes. Intercept value is 4. Or
Uh,
whatever be, it can be intercept B0 plus B1 X bar. So since here and X1 is a year, no, okay. Means that will be your YI hat. Means when it is not announced. Or you can say that here it will change the intercept, means it will increase the intercept. It doesn't have to be equal to intercept, it will be equal to B0 plus B1 XI. That will be the announcement, means no announcement, because in the in the three out of 4, 3 months, 2 months are not announced. That is what, or yes. So for 2 months, there is no announcement.
so then it can't take, let's say we have the same equation b naught plus b1 earn plus the error terms. Uh, like when earn is 0, that means b naught plus the
No,
error
not
term will
earn
be.
is not zero. Announcement is zero. Earn is still there positive. Earn is 4. When announced, it is talking about announcement. So announcement of earning and non-announcement of earning.
Oh, so like, is there a table below this where you can see how they?
Yeah, let's see. Yes, let's see. So here it is telling, intercept is 0.56, earn is 1.20. That is the beta. This one is B0, yeah, and this one is B1. B1 hat. Yeah, this one is B1 hat and this one is B0 hat. Okay, so that is what it is. And that is their standard error of coefficient. So standard error of B0 is this, standard error of B1 is this, and both are significant. Calculated test statistics, that is, it must be T because it is only one variable. So T. And how do I say it is T? Because this divided by this is T. So if you divide 0.5629 by 0.05, it will be 10.05. Divide 120 by 0.11, it will be 10.44. So these are T values. That is calculated T statistics. So that is the your model. With it is qualitative model. Okay. So let me explain you with the graph. Is there a graph? If there is no graph still, then I will explain. There is no graph. So let me explain you with a graph what this book is trying to tell you here. So here is the regression line, and this side is what is this? Earn is this side. The slope of earn. What is the dependent independent variable is what announcement. Okay, it is only about announcement, or where is the earn? This side is month and this side is earn returning. Oh, this side is return. Okay, so the test is earn is this side E, and even though there it was month, and this side is return. Okay, R return. It started with B 0.56, so I will put here 0.56, and the slope is more than 1, so I will draw a bit steeper slope, which is steeper. It is straight line, but steeper slope. Now, with announcement, that becomes like this. When there is announcement, then it comes out like this. So this one is with announcement. When dummy variable is equal to 1, so what is the dummy variable? Announcement and dummy variable. So let me type it. So this one is with announcement. Announcement of earning. So when the earning is announced, then the return becomes higher. And this side will be, actually month will be there. So earning will not be shown. It will be earning per month. So how is this graph? This one is month and this one is return. So where is earning? So month earning should be this. This is month, so month is here, and This is return. So this is not earning. Earning and return, return is profit. Okay, return for month without announcement, and mean return of the announcement of month. So that is the mean return of the announcement of month is around slightly above 5%. That comes out to be 0.53, and that is your B0. And then mean return for non-announcement month. Non-announcement, yeah, this one is mean return for non-announcement month means it is stationary. Data is stationary, and this one is the mean return for announced month, the upper one. So if there is announcement, then the mean return increases. That is what it wants to point out. So the correct diagram should be let it remain month, not that it has to be earning, though I had used to explain, but this one is time, T, time or month. So, so the announcement changes your earning this way. That is what this dummy variable tells. Otherwise, earning without announcement. This one is without announcement. And this one is announcement or with announcement. So let me place slightly here. And then, okay, announcement. Oh, okay, there is only one N. What? The spelling is announcement. Yes. So announcement of earning, and this one is without announcement of earning, without announcement of earning. So that's how the qualitative or dummy variable impact is shown. Either it will change the intercept, here it is changing the intercept, or it can change the slope. Means if it changes the slope, then your graph will become like this. It is changing the slope, so it will become like this. Yeah, but here I am not, since the book is not showing, so I don't want to confuse by pointing out this. Here it is showing that intercept is changing. Yeah. So that's how with the passage of time will change. Earning return will change. Is it clear, Yogi?
Yes,
Uh,
sir. Yes, sir.
okay. If it is clear, so return of earning announcement month is 1.77, and the return of non-earning announcement is 0.5629. That is what you had said B0. And the difference in mean is 1.20. So here the data has been made stationary, means it is showing uh, only the difference between earning and earning with announcement and earning without announcement. Okay, let's go down. What does it tell? So this we already discussed. Test of hypothesis, level of significance, and p-value. So you had studied p-value. What was the p-value?
So, p-value is
The minimum probability of rejection of H0.
yes, sir.
Yes, if we are rejecting, then that is the minimum probability at which we can reject H0. So, okay, so question set. Okay, we will solve all the questions. Hmm. Here, let's see. I think you can answer very easily all these questions. Read it.
Julie Moon is an energy analyst examining electricity, oil, and natural gas consumption in different regions over different seasons. She ran a simple regression explaining the variation in energy consumption as a function of temperature. The total variation of dependent variable was 140.58 and explained variation was 60.16. She had 60
Hmm.
monthly observations.
So explain variation was means what is this? SSR?
Yes, sir. Total
And
variation
this
is
one is
one.
SST.
Yes, sir.
Okay. So now, and how many N? So how many N minus 1 degrees of freedom?
So 59.
59. And for this degrees of freedom is only 1. Yeah, because we have only one, we know. Is an energy explain electricity. Well, So she ran a simple regression planning the variation in energy consumption as a function of temperature. So there is only one beta, B1, beta 0 is intercept, but slope is only one slope. So calculate the coefficient of determination, R square.
R
Coefficient
square
of
is explained variation by total variation. So
mean,
60
mean explained variation
variation.
by error total. R square is mean, okay, yes. So explained by total, so 60 by 140, okay.
Yes.
So 60 by 140 is a 0.42. Very good. R is that, okay. Now, next question. Calculate F testing. How will you calculate? Here is your test.
Here,
Fir- Here is your first. It will be
first
less.
numerator is mean explained variation. So 60.16
60.16.
divided by 1, 2 minus 1, which is 1.
Yes, which is 1, okay. And this divided by?
Divided by 140.58 minus 60.16.
Why 140.58?
So that is we need to get the like
F in,
SSE no sir. So
so you will have to 80, no? It will
TSS
be
minus
80.32, no?
sir subtracting sir 140.58 minus 60.16.
Yeah, so that will be 80.3,
Yes sir.
80.442. This divided by what are the error degrees of
So
freedom?
n minus k minus 2 k minus 2, so
58.
60 minus 2, so 58.
Yeah, 58. Okay. So how much does that come?
So 61.16.
It should be around 40 or something.
43.38.
43.38. Okay. 43 point. Very good. Correct. Now calculate the sample standard deviation. Okay. So sample standard deviation.
Uh, Here they given
Total variation means
by
this
y minus y bar
divided
the
by
whole square by n
n
minus 1
minus 1 square root.
square root. Yes, sir.
Yeah. So 140.5, how much does that come? 140.58 divided by 59 and a square root.
Sir, my doubt is like where we should take n and where we should take k, sir, because
So K is that of no, as many betas, so many K's. As many slopes, beta 1, beta 2, these are K's.
okay, sir.
Yeah. So here you are calculating total standard deviation. So what was your question? So
So
K,
like in calculating f statistics in the numerator we are taking n minus
K.
1, but in the denominator we are taking k minus 2.
No. You are in the numerator taking K.
Oh, numerator we are taking k. Okay.
K is only 1 here, no? So
Okay.
60.1 divided by 1.
Okay, divided by n minus 2.
Yeah, n minus 2 because n minus k is 1
Okay, sir.
and n minus 1 is degrees of freedom.
Okay, sir.
n
Okay, sir.
minus k. So k is only 1. So
Okay, sir.
that's why
Okay.
you divided by n minus 2.
Okay. So here we should take 60 minus 1
1.
for
Because we are
standard
calculating
deviation.
total.
Total.
Yeah. So 140.58 divided by 59 square root. So how much is 1.544? Yeah. This is the answer, 1.544. 2.86 is the variance. Is it clear?
Yes, sir.
Okay, question number 4. Hmm.
An analyst is interested in interpreting the results of and performing tests of hypothesis for market model estimation that regresses daily return on ABC stock on the daily return of the fictitious Euro Asia Africa equity index is proxy for the stock market. He has generated the regression results presented in the exhibition 27. Now, if the critical t values are plus 1.96 at 5% significance level, is the slope coefficient different from 0?
Okay, so it is asking for beta 1 or B1. So standard error of estimate standard deviation of ABC returns, standard deviation equity index return, number of 1200. Oh, intercept. Oh, okay, here is slope. Slope is 0.982. So is it different from zero? So 0.892 divided by what? The standard error of estimate is 1.26. So we have to divide this by 0.982 is B1 divided by SEB1. So SEB1 is sigma xi minus x bar whole square. This by xi minus x bar whole square. Do we have that information? We must be having a standard error of estimate, not the standard error of slope. Hyper estimation of market model. So this one is a standard error of estimate, SE. Is it SE of beta or is it SE of total? Not very clear. Otherwise, so 0.982 looks significantly different from zero, but how to calculate T? T will be this minus 0 divided by SE beta 1. SE beta 1. So this divided by 1.26 divided by, it is already standard error. A standard error of estimate. But it is different from a standard error of beta. Otherwise, let's see whether it is the standard of beta or it is the standard error of the model. Let me see. Probably we first need to calculate the variation of the independent variable using the standard deviation of the independent variable. Means this divided by xi minus x bar whole square, that divided by n we will have to calculate. So that's a bit longer. Xi minus x bar by n minus 1. So it has not, information has not been given.
Oh, sir. So they have just modified the formula, sir. Like x
Huh?
minus x by the whole square by n minus 1 multiplied and divided by n minus 1.
Yeah,
So
so to calculate xi minus x bar whole square. Oh, okay, so you are saying that we have this
they have just
0.70 times 1200
199.
minus 1.
Yes, sir. That's all.
So that gives us the xi minus x bar whole square. So we still need to calculate this. So how to calculate this?
So like they have given summation xi minus x by the whole square by n minus 1, which is 0.7.
Yeah, yes.
Oh, so no, sir. That is root
Yeah.
of that. No,
Huh?
that is root of that, right?
And this one is a standard deviation. Oh, yeah. It is a
Root
root
of
of
this
standard
value.
deviation square root variance. No. So xi minus x, okay. So he did this a square, no. 7.7
Oh,
square.
0.7 square. Okay, okay, okay. That
No,
makes sense.
no, it is
Okay,
correct.
yeah,
The 0.7 square times 1199.
okay, okay. Then it makes sense, sir. Okay, sir.
Yes. So then stand 1.26 divided by under root sigma xi minus x bar whole
Okay.
square.
That we
So
found.
that gives us the standard error of beta 1. Now we can easily calculate. So 9.982 minus 0 divided by this. So this will be significant. T is how much? About 20, 19 something. 19, it should be around 19 something.
18.9.
18.9, okay. Yes, 18.9. So we reject the null hypothesis. We reject the null hypothesis. Okay. So what was to be learned here? That how to calculate S beta 1 hat. We have the standard error of model. That is the standard error of the entire model. And we need to calculate for one beta 1, which beta 1 hat standard error. So beta 1 hat standard error is model standard error divided by under root sigma xi minus x bar whole square. We had studied this earlier, but we said that, well, the software will anyway calculate and give you. So you don't need to remember it, because software, if you type it in Python, you will get this result. You will already get below T, you will get this standard error of B. Means below, you will get T value rather. Either you get the standard error and then you get T. You get both values. The software automatically calculates, it will calculate beta 1 here, and then below that it will write your SE beta 1, and then it will write T value also. So software gives all this. I had seen this in Excel. So it will give all the three values, and you can easily check it. The problem with multi-collinearity happens that F is highly significant, but these T's are insignificant. And that is how multi-collinearity is detected. And then VIF is also there to detect multi-collinearity. Okay. Now, okay, question number 5. Yeah, okay, from 1. Now it is not 0, it is asking for 1. So what will you do?
So from
Here it will
one,
become 0.982 minus
1.
1.
So,
So it will be not different from 0 because it becomes what? 0.0018.
so what is it actually here trying to say? So, like the slope coefficient is different from 1 or
Yeah, is the slope different from 1? And the answer will be no.
so then I'm asking like what is the like,
It's 0.
how is the visual representation of this? So, like in the graph, is the
In
slope
the graph,
coefficient
the slope
different from?
coefficient is 1 means in the graph it will be just 45-degree line.
Oh, okay. So,
Yeah.
in the previous case, how will it be, sir?
In the previous case, that slope will be like this, and then you reject H0.
Okay, sir. So that means it's not close to 0, but something more.
Yes.
Okay.
So here T will be insignificant. The calculated slope coefficient is equal to 1. The calculated test result, let's see. So what is the T statistics? Minus 0.3463 is within the band. We fail to reject H0. Okay. Question number 6. Oh. Hmm. So this one is
Economists collected the monthly.
let's read the question first. Then what does it want to ask? What is the question? Oh my God, too long, too long data. Explain how the data. Too long question. Okay, explain how the data affected the results. The 2 is an outlier. Oh, okay. So with outlier and okay, so let's see what happens. So let's see R square. So in this case, here is the outlier. Yeah. And here also is the outlier. The rest of them are non-outlier. Okay. So what happens? It was the error. Now our R square is still pretty high. Standard error is this. The economics calculate correlation between the two returns was 0.996. The correlation R is 0.996. Okay. So R square is this. This square becomes this. So 0.996 square is 0.9921. Now what happens? Sum of square residual, let's go down. Mean F. What about F test? F is 500. Okay. Now let's calculate. When reviewing the result, and Dia Fuller suspected that they were unreliable. Okay. She found that the returns of month 2 would have been 7.21 and 6.49 of the large values shown in first table that we pointed out. Connecting these values resulted in a revised correlation of 0.82. So correlation is now smaller, much smaller than 0.996. So now it is 0.824. So the outlier had increased the correlation because outlier was much bigger. So it wants to tell that the outlier had increased the correlation to 0.996, and these two outliers actually weighted a lot, 72 and 64. They are actually 15 times. So, and there are only 6 observations. Oh, here it is rather 70 times, and so they waited a lot. So if you have big outliers, then correlation will change. Means if R changes, then R bar square will also change, F square will also change, uh, standard errors will also change. So your decisions will be wrong. Now, what happened here? R square fell down because correlation fell down to 0.824. So R square is a square of that. So it came down here much smaller, and then F also is only 8.4. Earlier it was 5. P value is 0.04. Earlier it was 0. So all changed. F was how much here? 500. That fell down to 8. So that is what it's telling. Explain how the bad data affected the results. For month 2 is an outlier and lying far away from the other data, because this outlier was caused by entry error. Correcting, so R square is now lower after correction. This comparison, we already did that. Then this one is what? The standard error is also much lower, and at 5, what about F? At 5% level, both model fit well. The difference in the fit is illustrated in Exhibit 31. Is there any Exhibit 31? So, first fit is showing this. Here it is clustered, and this one is the outlier, which one was about 64 and here 72. So that outlier, okay, and rest are clustered. Obviously, there will be heteroscedasticity. So whenever we have clustering, but after fitting, this model is much better fit than this, and this doesn't look having any problem. Okay, prediction on the simple linear regression, you know it very, very well. And the prediction is that yi is equal to b0 plus b1 x bar. But then that is the point prediction. Then we will have this interval prediction. So we had calculated the standard error of beta I, beta 1 hat. So we will have that added to point prediction. Okay. To have interval prediction, like let's go to the book. You know this very well, so that's why there is not much to add. This is that is how we predict, and this one is the point prediction. But then we can make interval prediction, means where is our standard error. So we will have this 1.6 plus minus 1.96 standard error or 96% confidence level. So that becomes a standard. This is the square of forecast. And so standard error is the same formula that we calculated right now. SE times 1 plus 1 by n plus xf minus x bar whole square by xi minus x bar whole square, sigma xi minus x bar whole square. So this one is our total variation, and this one is forecasted variation. So actually prediction technique is nothing new for you. So, and then we take this critical value of t, 95% confidence level, depending upon it, how much will it be. So it tells us that predict the value y, value of y as yf hat given the forecasted value of x and xf. Xf is given, and on that you predict. Then choose a significance level alpha. That will be 5% or 1%. Alpha, or confidence level 95% or 99%. Then determine the critical value of prediction interval, that is 1.96, or if it is 95%. If it is 99%, it may go to 2.7. Then compute the standard error of forecast, the same formula that we used, this formula Here was this formula, standard error of forecast, then multiply it into T alpha by 2. So, and then compute 1 minus alpha. So compute the standard forecast and compute the 1 minus alpha percent prediction interval for y hat plus minus T alpha by 2 standard error. So here is the example. So this is the example for ROA regression model. Given the forecasted value of capex is 6, means this is our x, and the predicted value comes this way. How? Because we have 4.87 is our B0 plus 1.25 times 6, and that gives us this value. Okay, YF. Now, this is point prediction or point estimate. Interval estimate with how much confidence? 5% significance means 95% confidence level. The T values for two-tailed are 2.776 because degrees of freedom is small. Had it been 30, then it would have been 1.96. So what is the standard of forecast that has been calculated? The standard error of forecast that comes out to be this. So we will multiply T alpha times this. Here we did plus minus 2.776, which is our T value. This T value, yeah, here, and then multiplied by this alpha, a standard that we can, sorry, standard, not alpha. We calculated, and that gives us point prediction plus minus. So this is our interval prediction. Yeah. Did you learn anything? Probably no. You knew this. Yeah.
Yes, sir.
You knew this. You knew this very well. Interval prediction. And then it is telling us that if we graph, it will be like this, means it is becoming wider. So here at the mean, this range is thinnest or smallest, and as we move away from the x bar, our prediction value of y interval prediction will vary. So upper bound of 95% prediction interval is this one. So from here it is varying. Here also it is increasing. It is becoming wider. If we go left or right of the mean, our interval will be wider. So upper value and same way lower value. So lower bound of 95% prediction and it got wider. This is our actual predicted value, the green one. That should be. This one is one standard error above the mean, and this one is one standard down below the mean. So question set. What is the coefficient of determination? Okay, let's calculate. What is the coefficient of determination for this regression model? Coefficient means R square.
R square.
So what will be your R square?
So total, so this 576.148 divided by 2449.
Very good. Very good. So that will be around 23.52%. What is the standard error of the estimate of the regression model?
So root of the total divided by n minus 1.
Root of the total error divided by n minus. That will be standard deviation. What is the standard error of the estimate for this regression model? Okay. So root of the total divided by n minus 1, how much does it come? It is 198. So it will be around 25. The thing is, oh, here is the mean square error. It is given, no? Mean square error is 19.19, and then so the square root of that.
Square root of that is
yeah, it has already been given. What you gave her, it was already given. Like what you said that this divided by n minus 1. So n minus 1 is n minus 2 because 1 is taken away. So it was 100, so n minus 2 actually. So error divided by n minus 2, that came here. So this is the variance. And so square root of that. Okay. Question number 3.
Sir, at 5% level of significance, do we reject the null hypothesis of the slope coefficient equal to 0 if the critical F value is 3.938?
Okay. So the critical value is 3.938. That is the critical value of F. Okay. So we calculate F. Let's calculate F. How to calculate F? We have this mean sum of a square. Oh, this. We have already regression mean sum of square and then error sum of square. So this divided by 19, we will easily get F. This is already we have calculated mean error. So 5 yes, we reject. Let's see. It comes out to how much? About 30. How much does F come? Okay. So F is 30, yeah. F is 30, 576 by 19, and critical is only 3.9, so you reject, we reject the null hypothesis. Question
Sir,
number
here, what is the difference between 1873 and 19.11, sir?
What is the?
In the table,
Okay.
scroll up there. Sir.
Yeah, this table, no?
Hi, sir. So, what is the difference between 1873 and 19.11?
Once again, what is your question? What is the difference between?
This 19.11 and 1873.5615. Like,
Oh, this one. Oh,
yes, sir.
this one is the total sum of squares.
Sir,
Total
sum of
squares
squares is 2449, sir.
1819. No. Oh, sorry. Error sum of square. This is SSE. Let me type it. This one is SSE.
Okay, sir.
And this one is SSR.
Yes, sir.
And this one is
Yes, sir.
SST.
Yes.
Okay. So R is R square is SSR by SST.
Yes, sir. Yes, sir.
Clear?
That is clear. Sir.
Then 1 minus this SSC by SST will give you also R square. Yeah. And here it is the mean square, since there was only one beta, so degrees of freedom was 1. So mean SSR is this, and this one is, so this divided by 98 is your mean square error.
Okay.
So this one 19 is equal to 1873 divided by 98. Okay?
Yes, sir.
Because it is mean. So mean will be divided by degrees of freedom.
Okay.
Okay. So we go to that. At 5, we do the null hypothesis. Now, evaluate the simple linear. So what is your result? Is it fit? Good fit. F is significant, so good fit. How much is R square? R square is not very good. R square is how much? What was our R square? R square was 23%. So it is not good fit. So R square says that 23%. Is it cross section or is it times? It looks like this cross section. Question: suppose you have a cross sectional. So if it is cross section, then R square will be low, and it is significant. So we would say that okay, is there any problem? So based on the above, F test, it passed the test. So the coefficient determination indicates that variation in the dependent only 23%, means that variation in the independent variable explains 23.52% of variation in the dependent variable. So this part is very much important, many people know. So variation of the dependent variable is 23.52%. How much is the variation in independent variable? 1 unit. variation, 1 unit variation in the independent variable explains, oh well, if it is in percentage, then 100% variation. 1 unit, no. 100% variation will be doubling. So no, 1 unit of variation will explain 0.2352% change. That is what I know, 0.2352 change. So increase x by 1, y will increase by 0.2352. Also, if a statistic confirms that the slope coefficient is different from zero at the 5% level, in sum, the model seems to fit data reasonably well. So far, okay. Now let's go to question number 511. Okay. What is the question number 5? What is the predicted value of NPM if the forecasted value is 5? I think you can easily do it, no? So if it is 5, so what will be predicted value? 16.5 minus
minus 1.3
3 into
into
5, so
5.
6.5, so 10. And does it tell us to calculate interval? It is 10. Okay. What is the standard error of the forecast SP if the forecasted value of RDR is 5? Standard error. Okay, let's see. Because standard we need to calculate, we didn't use that formula. So, yeah, well, we didn't ever try because software will do it, so we didn't do this. But anyway, this is the information. I'm not sure if you will it be asked in the exam. Probably they will give you this formula because there is no point in remembering such a long formula. That SE times 1 plus 1 by n plus this y minus y bar whole square divided by sum of xi minus x bar whole square. So I don't get question number 7. 95% confidence interval if it is 2.44. So you will do it very easily, no? Means you will multiply 2.44 by this 2.149. So what is our beta? We had predicted 10, no doubt, but then 95% confidence interval will be, so this is our critical T value, no, 2.44. And standard error is this 2. So about 4, 2 times 5. So we will have 10 plus 5 and minus 5. So it should be 15 and minus 5. Let's see. It should be between 5 and 15 or well, 4 and 16. That is what it should be. 10 plus minus 2.447 times 2.14. So yeah, 4.73 and 15. That is what I had said. Interval estimate. What is the predicted value of NPL if the forecasted is 15? Do you want to do this?
Sir, it's
So model is here.
see,
15
that same thing, no, sir. Like instead of 5, you have
15
to
times 1.3 will be how much? 19.5. Minus 19.5, it will be minus 3.
minus 3. Yes, sir.
Where is this? Question minus 3. Okay. Let me see what again a long calculation. But what does it tell? Referring to exhibit 9, what is the standard error of forecast if the forecasted value of RDR is 15? So here we have another beta one. B1 is 15. Well, no, B1 is the same. XI is 15. So in that case, what will be the forecast of the? Okay, let's go down. This tells us so SF comes out to be at this. Okay. And then 95% confidence, then again we will have 2.4 times this, and we had minus 3, no? Minus 3 plus minus this. Same repetition. Okay. Now we will calculate 11. Calculate the Sample variance of the dependent variable using information in the table. Okay, so what is this table? Yeah, please read it and then we will see. From here, read the question.
So, you're examining the results of regression estimation that attempts to explain the unit sales growth of a business you are researching. The analysis of variance output for a regression is given in the table. Regression was based on 5 observations.
Okay, so N is 5. The regression was based on 5 observations. Now we have degrees of freedom, sum of squares, mean sum of square. Everything is calculated. Residual is degrees of freedom 3. So 7.2 divided by 3 is 2.4. F is 88 divided by 2.4 is equal to 36. And P value is this. So everything is given actually. So what is the question? Calculate the sample variance of the dependent variable using information from the above. So sample variance. So we have residual is 7.2. That was a sample variance, no? So variance is sample variance of dependent variable means we have to calculate what we have to calculate. We have to calculate sigma. Let's see if we can. We have to calculate S. Sorry, S big sum y yi minus y bar. So y bar whole square divided by 4. That will be our sample variance. Now, how to figure that out from this information? Yi minus y bar to the power squared whole divided by 4. So, oh, sorry. I haven't seen the answer yet, but I still want to do it like this. I want to type it here in bracket because the formula is not. What is happening? What is happening? This divided by this. So there should be parenthesis and all divided by n minus 4. Okay. So can you figure out? We should be able to figure out. So total sum of squares is 95.2. But this one is what? Output. Is this dependent variable or independent variable? What are we talking about? Output is dependent. Let's see. Let me read the questions once again. You are examining the result of regression estimation that attempts to explain that unit sales growth of business you are researching. The analysis of variance output for the regression is given in 37. The regression was based on 5 observations. Okay. So n is equal to 5, degrees of freedom is 4. So I think sample variance should be simply that divided by 4. Total variance 95.5 divided by 4. That should give us the variance. So how much will that be? About 24, 23 point something. Let's see, is that the answer? In the sample variance is, 23.8. Because total variance divided by n minus 1. So okay, coefficient determination you can easily calculate, means r square. What will be r square?
R square 88 by 95.2.
Very good. What has happened? What? Is there some problem here? Okay, now it is charging. Is it charging or not?
No, sir, it's still not happening.
It is charging okay, sometimes it charges and then it doesn't. What is the problem? Now it is charging. Okay. There was some problem with the. What about this one? Hmm. This one is also charging. Okay. So good. Looks like life is good. Hmm. Now we have been okay. So R square you calculated correctly. And then what is the hypothesis? What hypothesis does the F test? That beta 1 is not equal to 0, or beta 1 is equal to beta 2 is equal to 0, not equal to. All slope coefficient is in a linear regression are equal to 0. Is the what is your answer to question 14?
Is the 10
We have F,
36.67.
yeah, we have F36. So
So
it
p
is,
value is less than 0.05, so we reject.
it is significant. Yes, very good. Very good. So if tabulated value is P value. Calculate the standard error of estimate. We calculate standard deviation and standard error of estimate. The square root of that, what we have calculated.
2.4.
Yes, the square root of 2.4 is 1.54. So we had here 2.4 we had. So mean the sum of a square. So this the square root of that is the standard error of estimate. Oh my God, this is too much. What do you want to do? This chapter was really very long. You want to study or you want to finish it tomorrow?
Tomorrow, sir, since there are 40 questions also.
40 questions also. So, and tomorrow's chapter is very small. We can finish that in 1 hour or less. Okay, so we will finish tomorrow.
Okay.
Oh, my God, it is too much. What is the functional form of symbol? Yes, it is important. Log, ln, log, all those things will
All
come.
those things.
Yeah, so let's just stop here. We couldn't finish this. But anyway, stop recording. Oh, so this chapter was really too long. And but it was informative, no? You
Yes,
learned,
sir. Yes.
yeah, learned a lot of things and now
Lots
you
of formulas.
lots of formula, lot of concepts that now you can calculate F R square, beta correlation from correlation to beta, from beta to correlation. You can all calculate all those things. So that's why I thought we will learn a lot of things, even though you have studied simple regression for many years. So, okay, we will see tomorrow also. It will be end, the book will end tomorrow.
Okay.
Okay, good night.
Thank you, sir.
Welcome.